Imagine taking the world's most pristine, highly guarded database, like, Fort Knox for data.
Right, the absolute gold standard of security.
Yeah. And then you just turn on all the surrounding walls, you fire the database administrator, and you let thousands of strangers basically scream at each other in a public square to decide what data gets saved.
It sounds like an absolute engineering nightmare. I mean, on the surface.
Totally. You'd expect total chaos, right? Constant data corruption, a system that it should completely collapse under its own weight within minutes.
Oh, absolutely.
But today, we are looking at an architecture where that chaotic public square somehow perfectly agrees on the exact same version of the truth, and all without anyone actually trusting anyone else.
Which is wild.
Yeah.
It really forces a complete mental reset for anyone coming from traditional systems engineering. I mean, the entire concept of how we define a database is just turned inside out here.
Right.
Because you're taking a system where trust is normally localized in a single authority, like a primary server, and you are distributing that trust across, well, mathematics and game theory.
Which brings us to our focus. Welcome to a new deep dive into our source material. Today, we're tearing down the buzzwords surrounding blockchain fundamentals.
Yes, getting past all the noise.
Exactly. Because if you're listening to this, you might be a developer prepping for a massive infrastructure pivot. Or, maybe you're a CTO trying to separate the actual reality from sales pitches.
And our source document today is tailored exactly for you. It's this highly technical, systems-level engineering manual.
So we are throwing out the marketing hype.
Gone.
We are ignoring token prices entirely, and we are definitely not giving financial advice.
Definitely not. Our mission here is to analyze this technology purely as a distributed state machine.
Okay, let's unpack this, because it is incredibly satisfying to finally peek under the hood of a technology that everyone talks about, but let's be honest, few people truly understand at the nuts and bolts level.
Yeah, it's mostly just buzzwords for most people. So we're going to open up the data structures, map out the network mechanics, and really confront the very real, very harsh engineering trade-offs that make a blockchain actually function.
Because the goal is to equip you with the technical literacy to understand the physical and mathematical limitations of these systems. But before we look at the individual gears, we need to agree on what kind of engine we're dealing with, right?
Absolutely. We need a foundational definition that doesn't rely on all the jargon.
And the source manual provides this very rigorous 5-part definition that it carries a lot of architectural weight.
It really does. It defines a blockchain as a replicated, append-only ledger whose entries are grouped into blocks, where each block cryptographically commits to the one before it.
And maintained by a peer-to-peer network of independent nodes.
Right, nodes that agree on a single ordering of those blocks without trusting one another.
I mean, every single word in that sentence is load-bearing. If we pull it apart, that first word, replicated, that stands out immediately as a massive departure from standard practice.
Completely.
Because in a traditional AWS or Azure cloud setup, you might have a primary database instance, maybe a read replica, and some offsite backups. You are minimizing redundancy to maximize efficiency, right?
Yeah, you want to keep it lean. But here, the manual implies we're forcing every single participant on the network to maintain a complete independent copy of the entire historical ledger.
Thousands upon thousands of full copies stored on physical hard drives all over the planet.
It's massive duplication.
Yeah.
And then you add the append-only constraint.
Right, which is huge.
In a standard SQL database, you can just execute an update or delete command.
Yeah.
If a user changes their address, you overwrite the old data. Done.
But on a blockchain, those commands literally do not exist at the protocol level.
They don't. If a mistake is made or a state changes, you cannot reach back into history to rewrite it. You can only append a new transaction at the very tip of the ledger that corrects the state moving forward.
And we aren't streaming those new transactions to the database continuously, like 1 millisecond at a time either?
No, the definition specifies that entries are grouped into blocks.
Grouped into blocks. That suggests a mandatory batching process. We are scooping up hundreds or thousands of transactions, wrapping them in a package, and then attaching that package to the ledger.
Right, and the method of attachment is where that cryptographically chained part comes in. The system uses hashing algorithms to weave the data of the new block into the data of the previous block.
So any attempt to tamper with historical data becomes mathematically glaring to everyone observing the network.
Exactly. It's a giant alarm bell.
Yeah.
And finally, all of this is managed by a peer-to-peer network with no trust.
Meaning there is no master node.
None.
Oh.
There is no super user with administrative privileges who can force the network to accept a change.
The source text offers a mental model for this that I think will resonate deeply with the software engineers listening. It frames a blockchain as essentially a global Git repository that the whole world shares.
Framing it as Git is a brilliant translation of the architecture.
Right. For anyone not writing code daily, Git is the version control system developers use to track changes in software. You write some code, you create a commit to save those changes, and that commit permanently points back to the previous version of the code base.
So the manual is telling us to imagine a global Git repo, but with extreme constraints. Commits are forced into these batched blocks.
And the history is mathematically locked.
Right. And instead of a lead developer or a project maintainer reviewing pull requests and deciding what gets merged into the main branch.
A decentralized protocol of blind consensus rules dictates the canonical truth.
What's fascinating here is how this immediately forces a CTO to confront the efficiency trade-off.
Yeah, let's talk about that.
When you map this architecture against a traditional database sitting behind an API, you realize you're sacrificing almost every metric of performance. You are giving up high throughput. You're giving up low latency.
And multiplying your storage costs by tens of thousands. I have to play the skeptic here for a second, because if a junior engineer pitched this architecture to me for a standard application, I would laugh them out of the room.
Oh, you'd fire them.
Literally.
Yeah.
We're taking a perfectly good lightning-fast database, cloning it thousands of times across the globe, and deliberately crippling its speed down to maybe a dozen or a few thousand transactions a second. From a purely traditional systems perspective, this looks like the worst software design ever conceived.
If your objective is simply to store and retrieve data quickly and cheaply, it's a terrible design.
Right.
But the manual emphasizes that performance is not the objective here.
Right.
You are intentionally paying that massive, steep performance penalty to purchase two highly specific properties that a centralized database can never offer.
Trustlessness and censorship resistance.
Exactly. You are paying to remove the database administrator.
We are building a hyper-redundant, deliberately sluggish machine for the sole purpose of ensuring that no single government, corporation, or individual can turn it off, censor a transaction, or alter the historical record.
That is the ultimate business calculation. When a company considers integrating blockchain, the leadership must ask themselves if their specific use case genuinely requires trustlessness and censorship resistance.
And if the answer is no,
then they should stick to a centralized database, seriously. But if the answer is yes, they have to accept the inherent friction of this technology.
okay, now that we understand we are intentionally building this heavily replicated batched system, let's actually open up one of those batches.
Let's do it.
We need to physically dissect a block to see how this magic trick is actually performed. And here's where it gets really interesting. The manual conceptually splits a block into two distinct structures, the header and the body.
And understanding the separation between the header and the body is the key to understanding how the entire network scales. The manual uses Bitcoin's architecture as the foundational example here.
Yeah, Bitcoin uses an 80-byte header. 80 bytes.
It's tiny.
It is infinitesimally small. It's the size of a short text message. But the body of the block, the actual payload underneath that tiny header, can be megabytes large because it holds the raw data of thousands of transactions.
So the header is a fixed-size piece of metadata, while the body is variable depending on network traffic. But the header is the critical component.
Why is that?
Because the network doesn't actually chain the bodies together, it chains the headers together. The header contains the cryptographic proof of everything that happened in the block.
Okay, so let's put those 80 bytes under the microscope. The source highlights several fields, but 4 of them are doing the heavy lifting. The first one we need to understand is how you cram megabytes of transaction data into a tiny header.
Right, and that is achieved through the Merkle root.
The Merkle root.
It's an elegant application of cryptography. Think about it. If a block contains 2,000 transactions, the protocol does not hash all 2,000 transactions into one massive, unstructured blob.
That would be messy.
Extremely. Doing that would make it incredibly difficult to verify a single transaction later on. So instead, the protocol structures the transactions as the leaves of a binary tree, specifically a Merkle tree.
I want to make sure we visualize this clearly for you listening. Imagine an upside-down tree. At the very bottom, you have 2,000 individual leaves, which represent the raw transactions.
Right.
The protocol takes transaction A and transaction B and runs them through a cryptographic hashing algorithm like SHA-256 to produce a single output hash. That forms a branch.
Yeah, and then it does the exact same for transaction C and D to form another branch.
And it just continues pairing and hashing horizontally across the entire base.
Exactly. Then it moves up a level, it takes the hash of AB and pairs it with the hash of CD and hashes those together. It repeatedly collapses the data, moving up the tree, having the number of hashes at each tier.
Until you finally reach the very top of the tree, the trunk, where you are left with just one single 32-byte hash.
And that is the Merkle root.
Wow. And that single fingerprint is what gets placed into the 80-byte header.
By doing this, the Merkle root acts as an airtight cryptographic seal for the entire payload. If you change a single comma in transaction A at the bottom of the tree, its hash changes.
Which means the branch hash changes.
Yes, that changes the AB branch hash, which propagates all the way up, completely altering the final Merkle root in the header.
I see the security benefit for sure. But why go through the trouble of building the tree structure? Why not just hash the whole list of transactions sequentially and put that single hash in the header? It would still provide the same tamper-evident seal, wouldn't it?
It would, but the tree structure is what allows for light clients. This is a concept the manual emphasizes for mobile and resource-constrained devices.
Oh.
If you just hashed a flat list and a mobile phone wanted to verify that transaction D was in the block, the phone would have to download all 2,000 transactions to run the hash itself.
Which would kill the data plan.
Exactly. But with a Merkle tree, the phone only needs to download the 80-byte header plus the specific sibling hashes along the branch connecting transaction D to the root. It's a logarithmic reduction in data.
We'll explore the mechanics of that later, but the separation of the Merkle root into the header is what makes the network usable for regular people. That is incredibly efficient.
It really is.
Okay, the next critical field in that tiny header is the timestamp. Now, coming from a traditional server environment, I expect a timestamp to be an authoritative atomic clock measurement of exactly when an event occurred, down to the millisecond.
Well, this raises an important question about the reality of decentralized timekeeping.
Okay.
In a network of tens of thousands of independent computers scattered across different time zones, running on different hardware, there is no master clock.
Right, because providing a centralized time server would introduce a single point of failure.
Exactly. Therefore, time on a blockchain is an approximation.
The manual literally says on-chain timestamps can be off by hours. To a developer building a time-sensitive smart contract, that sounds terrifying.
It is a major gotcha for developers. The timestamp is simply a Unix epoch time injected by the miner who constructs the block.
So they just guess.
Well, the protocol enforces loose parameters to prevent extreme manipulation. For instance, the timestamp must be strictly greater than the median time of the previous 11 blocks, and it cannot be more than a couple of hours in the future, according to the node receiving it.
Right. But the takeaway for a CTO is stark. Never build an application that relies on an on-chain timestamp for precise wall clock execution.
Exactly. Decentralized time is inherently squishy.
Squishy time. It's a great reminder of the weird physics of this space. Moving on, the next two fields are the difficulty target and the nonce. Now, these are heavily tied to proof-of-work consensus, like Bitcoin uses. While we aren't doing a full consensus deep dive today, we have to explain what these numbers are doing inside the header.
They represent the cryptographic puzzle that creates the network's security barrier. The difficulty target is essentially a threshold dictated by the protocol. It tells the network the final hash of this 80-byte header must be a number smaller than X.
And since a cryptographic hash is essentially a random number, the only way to get a hash smaller than the target is to keep changing the input data and hashing it over and over again until you get lucky.
Right, but you can't change the Merkle root and you can't really change the timestamp too much.
Which is why the header includes the nonce. Nonce stands for number used once. It is a dedicated, arbitrary field that the miner is allowed to rapidly swap out.
It's like a combination lock on a safe, but there's no logic to cracking it. You just spin the dial to a random number, pull the handle, and see if it opens.
If not, you spin it to another random number.
Exactly. The miners are just cycling through billions of nonces a second, hashing the header, hoping the output drops below the difficulty target.
And that brute force computation is the work in proof of work.
Yes, and the brilliance of the difficulty target is that it automatically adjusts. If more miners join the network and the blocks are being solved too quickly, the protocol lowers the target, making the puzzle exponentially harder.
So this self-regulating feedback loop ensures the system produces blocks at a steady, predictable cadence, regardless of how much computing power is thrown at it.
Precisely.
So we've constructed our header, we have our Merkle root securing the payload, our squishy timestamp, and our proof of work nonce. But a single block is just a solitary island of data. The defining characteristic of this technology is how these batches link together.
And that brings us to the final and arguably most vital
Yeah.
field in the header, the previous block hash.
The previous block hash.
It is the spine of the ledger. It
Yeah.
is the mechanism that transforms a pile of isolated blocks into a continuous chain. The protocol mandates that every new block header must contain the exact cryptographic hash of the block header that preceded it.
To really appreciate the security of this, we need to rely on the cryptographic primitives detailed in our source. We know hashes are deterministic, right? The same input always yields the same output.
Always.
We know they are collision resistant. It is practically impossible in our physical universe to find two different inputs that produce the same 32-byte hash. But the property doing the most work here is the avalanche effect.
Yes, the avalanche effect dictates that if you take a large data set and alter a single bit of information, just flipping a 1 to a 0, the resulting hash does not just change slightly, it changes completely and unpredictably.
Statistically, about half of the bits in the output hash will flip. Our sources provide a phenomenal analogy for visualizing this. Imagine a stack of numbered, heavy, wax-sealed envelopes sitting on a desk. Envelope 1, envelope 2, envelope 3. Each envelope represents a block. Now, here's the cryptographic twist. Pressed into the wax seal of each envelope is a highly detailed, miniature photograph of the entire preceding envelope.
That miniature photograph is the perfect physical manifestation of the previous block hash.
I love that visual. So let's walk through an actual hack attempt using this model. Assume I am a malicious actor. I want to go back in time to block 100, which was mined yesterday. I want to alter a transaction inside that block to route millions of dollars to my own wallet.
Okay, let's see how that plays out.
I sneak in, carefully slice open envelope 100, change the recipient address, and seal it back up. What happens structurally?
Well, the instant you alter that single address in block 100, the avalanche effect takes over. The hash of that specific transaction changes completely. Because of the Merkle tree structure we discussed, that altered hash bubbles up, changing the branch hash, which changes the trunk.
Meaning the Merkle root inside the header of block 100 is now entirely different.
Exactly. Which means the data inside the 80-byte header has changed.
Which means if you run a hash function on the header of block 100, the output is a completely new string of characters.
And that is exactly the problem for the attacker. Block 101, which was already sealed, has a wax seal containing the photograph of the original block 100.
Oh.
The network compares the photograph on 101 to the new reality of 100, and they no longer match. The cryptographic pointer is shattered. Every node on the network instantly recognizes that block 101 is attempting to link to a history that no longer exists.
So to hide my crime, I have to forge a new link. I have to open envelope 101 and stamp a new wax seal with the photograph of my tampered envelope 100. But the moment I change the seal in 101, I have changed the data of 101.
Yes.
Which means its hash changes. Which means the photograph on envelope 102 is now broken.
You trigger a catastrophic cascade failure. To successfully alter history, the attacker cannot just change one block. They must sequentially recompute the header for block 101, then block 102, then block 103, all the way to the present moment.
And in a proof-of-work system, recomputing a header doesn't just mean changing a text file. It means resolving that brutally difficult cryptographic puzzle.
Over and over.
It means finding a brand new valid nonce for every single block in that cascade.
If we connect this to the bigger picture, it fundamentally redefines how we use the word immutable in software engineering. People often describe blockchains as immutable, implying the data is etched in stone by the laws of physics. But the manual clarifies that immutability here is an economic and probabilistic property.
That is a vital distinction for a CTO. The data isn't physically locked in a vault where it can't be touched. Mathematically, it is entirely possible to change old data.
It is possible, but the system is designed to make it prohibitively expensive. To execute that cascading rewrite of history, the attacker would have to resolve all the proof-of-work puzzles for the altered blocks. Furthermore, they would have to do it faster than the rest of the honest network is adding new, valid blocks to the current chain.
They have to catch up to the present and overtake the honest chain.
Right. To do that, The attacker must command more than 50% of the entire global computing power of the network. This is the definition of a 51% attack.
You need to secretly build server farms the size of small countries, consuming gigawatts of electricity just to outpace the combined hash rate of the rest of the planet.
Exactly. And even if you shift away from proof-of-work hardware to look at modern proof-of-stake systems like Ethereum, the economic deterrence simply takes a different form.
The mechanism of consensus changes, but the economic ruin remains the core defense.
Yes. In a proof-of-stake system, hardware and electricity are replaced by locked capital. Validators deposit massive amounts of cryptocurrency as collateral. To execute a 51% attack and rewrite history on a proof-of-stake chain, you need to control the majority of that staked capital.
But unlike proof of work, where you just burn electricity, proof of stake introduces a direct penalty. If you try to rewrite history, the protocol can mathematically prove you are acting maliciously because you are signing conflicting versions of the truth.
That cryptographic proof of contradiction triggers a mechanism called slashing. The protocol automatically destroys a massive percentage or even all of the attacker's staked capital.
We are talking about billions of dollars instantly burned by autonomous code.
It's ruthless.
So whether you are paying in burned electricity or slashed capital, the reality is the same. Old data isn't magically unchangeable, it is just financially suicidal to try. And because of the cascading hashes, any attempt to do so is instantly tamper evident to everyone watching the network.
That brings us to a crucial operational question. We know the data structure is robust and heavily defended by cryptography and economics. But data structures don't run themselves.
Right.
Someone needs to physically host these files, run the hashing algorithms, and enforce these rules. Who is actually operating this massive global Git repository?
That plunges us into the network layer. A blockchain doesn't live in a Google data center. It lives on thousands of independent computers, which the manual refers to as nodes. Every node runs a client software implementation of the protocol, and they are connected to each other in a flat peer-to-peer P2P network.
The topography of a P2P network is critical to understand here. There's no master server routing traffic. There is no central hub. It is a decentralized mesh.
And the scale is massive. If we look around early 2026, Bitcoin maintains tens of thousands of reachable public nodes, with many more operating privately behind firewalls. Ethereum operates on a similar massive scale.
But our source is very careful to categorize these participants. Not all nodes are carrying the same weight. There is a specific hierarchy of participation based on a node operator's technical resources and their level of paranoia.
Right. The manual breaks them down into three primary categories. Let's start with the heavy lifters, the full nodes.
Full nodes are the absolute backbone and immune system of the network. A full node downloads every single block and stores the current state of the ledger. But more importantly, a full node independently verifies every single transaction against every single consensus rule.
I love the characterization of full nodes in the text. They are the ultimate skeptics. They trust absolutely no one.
No one at all.
If a miner broadcasts a new block, the full node doesn't just accept it because the miner has a lot of hash power. The full node rips the block apart. It recalculates the Merkle root. It verifies every digital signature. It checks the entire history to ensure the person spending the funds actually has them.
If a miner manages to solve the proof-of-work puzzle, expending massive amounts of electricity, but they sneak in a transaction that prints 1 million extra coins out of thin air, the full node software will instantly flag the consensus violation.
And then what?
The full node will drop the block entirely, banning the peer that sent it. The miner's electricity is completely wasted. Running a full node is how you individually project sovereignty over the rules of the network.
But projecting that sovereignty requires serious hardware. A pruned Bitcoin node is manageable, but an Ethereum full node requires over a terabyte of high-speed, solid-state storage, plus significant RAM and bandwidth.
Yeah, they aren't cheap to run.
These are typically run by cryptocurrency exchanges, infrastructure businesses, and dedicated privacy advocates. So if that is the standard full node, what is the next tier up?
The archive node. This is a full node taken to the extreme. A standard full node verifies all the math. But to save storage space, it routinely deletes the intermediate states of the network once they are proven valid. It only cares about the present balances. An archive node retains the exact state of the network at every single block in history.
Meaning an archive node can instantly tell you exactly what a specific wallet's balance was at block 14 million and block 14 million and one all the way back to the Genesis block.
Correct. The storage requirements for that historical granular data are immense. We are talking upwards of 15 to 20 terabytes, growing daily.
Wow.
The average user never runs an archive node. They are operated almost exclusively by blockchain analytics firms, block explorers like Etherscan, and major data providers who need to query deep historical patterns.
Okay, so that covers the massive data centers and the paranoid auditors. But if I download a crypto wallet on my phone absolutely does not have a terabyte of storage, nor does it have the battery life to hash thousands of transactions a second. How is my phone interacting with this decentralized mesh?
Mobile wallets and lightweight browser extensions operate as the third type. Light nodes, or SPV nodes. SPV stands for Simplified Payment Verification.
This circles back perfectly to our anatomy lesson earlier. The reason the protocol separates the 80-byte header from the megabytes of transaction bodies is specifically to enable these light nodes.
Exactly. A light node simply ignores the massive transaction bodies. It only downloads the continuous chain of 80-byte block headers. Instead of terabytes of data, a light node only needs to store a few megabytes.
Which any phone can handle.
Right. It allows a smartphone to mathematically verify the chain of work without downloading the actual payload.
I think we can build on our auditor analogy here. The full nodes are the deeply skeptical, paranoid corporate auditors who lock themselves in a room and recalculate every single receipt and expense report in the company's history by hand.
Yep, that's them.
The SPV light node is the busy executive. The executive doesn't have time to look at a million receipts. They just call up the auditor and ask, "Send me the one-page summary report. I just need cryptographic proof that my specific check cleared."
That analogy highlights the dynamic perfectly, but it also exposes the inherent vulnerability that an executive faces. When an SPV node wants to verify a payment, it connects to a full node and requests a Merkle proof.
Let's trace the math on that. If I'm the light node, I only have the Merkle root in my header. I ask the full node, "Prove transaction D is in this block."
Right.
The full node doesn't send me the whole block. It sends me transaction D plus the hash of its sibling, transaction C. I hash D myself, combine it with C, and get the branch hash.
And then the full node sends me the hash of the AB branch.
Right. I combine those, hash them, and if my final result matches the Merkle root I already have, the math proves transaction D must be in the block.
The math is airtight. But this raises an important question about security models. A Merkle proof only verifies inclusion. It mathematically guarantees the transaction is physically located inside that specific block. It does absolutely nothing to verify validity.
That is a terrifying distinction. What exactly is the difference between inclusion and validity?
Validity requires knowing that every other transaction in that block and the entire chain history preceding it obeyed the rules of the network. Because the light node deliberately ignores the rest of the block body, it cannot verify validity.
I see.
It cannot check if another transaction in the block was a double spend or if the miner inflated the block reward. The light node is fundamentally trusting that the full node providing the Merkle proof is operating on the honest, valid chain.
So if I am a light client connected to a malicious full node, that node could lie to me by omission. It could spin up a fake invalid chain in its basement, create a block where it gives itself $1 billion, put my transaction in that fake block, and hand me a mathematically perfect Merkle proof of inclusion.
Exactly. The math checks out, but the reality is totally fabricated.
And that is why the manual issues a stark warning to developers and CTOs. SPV light clients have a fundamentally degraded security model. For a consumer buying a coffee from their phone, the risk is negligible. But if you are building an exchange, a payment gateway, or a custodian handling millions of dollars in corporate treasury, you cannot rely on SPV nodes or third-party API providers.
You just can't. To eliminate trust, you must run your own full nodes.
So we have this vast heterogeneous network, tens of thousands of paranoid auditors and millions of lightweight executives, all scattered across the globe with no central routing server. When I sit at my desk, open my laptop, and click send on a transaction, how does that tiny packet of data actually reach all of those machines?
It navigates the mesh using the gossip protocol, which is technically known as epidemic broadcast. It operates identically to a highly contagious virus spreading through a crowded room.
Every node maintains open, persistent TCP connections with a random subset of other nodes, usually about 8 to 12 outbound connections. We call these its peers.
When your node receives a newly created transaction, its first action is local validation. It checks the digital signature and ensures the funds haven't already been spent. If the transaction is invalid, the node drops it silently.
This localized filtering ensures that spam and invalid data never propagate far into the network.
But if the transaction is valid, The node turns around and broadcasts it to its 8 or 12 peers. Those peers perform the exact same validation. If it passes, they broadcast it to their peers.
It's an exponential ripple effect.
Exactly. Within a couple of seconds, a single transaction floods the entire global network.
However, naive flooding would immediately collapse the network's bandwidth. If every node is connected to 8 peers and a megabyte-sized block is found, having 8 peers simultaneously shove a megabyte of identical data at you would saturate your connection instantly.
That's where the announce then fetch pattern comes in. It's essentially polite gossip. Instead of blindly sending the massive payload, a node sends a tiny inventory message to its peers saying, "Hey, I just validated transaction X. Do you have it?" The peer checks its local database. If it already received transaction X from a different route, it simply ignores the message. If it hasn't seen it, it replies, "No, send it over."
This cryptographic handshake prevents redundant data transfers and keeps the global bandwidth utilization remarkably efficient.
It's very smart.
So we've just blasted this transaction to 20,000 computers in 2 seconds. But it's not in a block yet. It's just floating out there in the ether. Which brings us to the most chaotic, cutthroat environment in this entire architecture, the mempool.
Ah, the memory pool.
Yeah.
It serves as the decentralized waiting room of the network. Every single node maintains its own local mempool.
Yeah.
It is an ephemeral holding area for transactions that have been validated by the node but have not yet been scooped up and confirmed inside a block by a miner.
Ephemeral is the key word there. The mempool is not the blockchain. It is stored in RAM. If you pull the plug on your node and reboot it, your mempool is wiped completely clean until it gossips with its peers and repopulates.
Exactly. And because network propagation isn't perfectly instantaneous, and because different node operators configure different RAM limits, no two nodes on the planet have the exact same mempool at any given millisecond.
It is a fluid, constantly shifting data structure. And for a user trying to interact with the network, understanding the mechanics of the mempool is critical because it is absolutely not a fair first in, first out queue.
Not at all. In a normal software queue, you take a ticket, you wait your turn, you get processed. But on a blockchain, block space is an artificially scarce commodity.
A Bitcoin block arrives roughly every 10 minutes and holds about a megabyte of data. An Ethereum block arrives every 12 seconds with strict computational limits.
So there are almost always more transactions sitting in the waiting room than there are seats on the next bus.
When demand for block space exceeds supply, the miners or block proposers have to decide which transactions get included. And because they are rational actors running a business, they are scanning that waiting room for the highest bidders.
The mempool is a brutal, public, adversarial auction.
It really is.
Every transaction includes a fee attached by the user. The block proposer sorts their local mempool by the highest fee per byte, grabs the most lucrative transactions until the block is full, and ignores the rest.
If you attach a cheap fee during a network spike, your transaction might languish in the mempool for hours or get evicted entirely if the node's RAM fills up.
The public nature of this auction introduces one of the most complex and predatory dynamics in decentralized systems engineering, MEV, or maximal extractable value.
Let's get into this because it's fascinating.
Because the mempool is unencrypted and transparent, everyone can see everyone else's bids before the block is constructed.
This transparency creates a dark forest where algorithmic predators hunt. Let's walk through a concrete example of MEV. Let's say I submit a transaction to a decentralized exchange on Ethereum. I want to buy a massive amount of a specific token. According to the automated market maker math, my massive buy order is going to significantly push the price of that token up.
Right. And as soon as your transaction hits the mempool, it is detected by automated arbitrage bots. These bots simulate your trade locally and realize your order will impact the market price. The bot immediately constructs its own transaction to buy the exact same token.
But the bot wants to buy the token before my order executes, at the currently lower price. So it attaches a slightly higher transaction fee than mine, effectively bribing the block proposer to put the bot's transaction earlier in the block sequence than mine.
This is a classic front-running attack.
Yeah.
The bot's buy order executes first. Then your massive buy order executes exactly as you signed it, which pushes the market price of the token up.
And the bot isn't done. In that exact same block, the bot submits a third transaction, a sell order, to instantly dump the tokens it just bought at the new artificially inflated price I created.
They sandwich your transaction between their buy and sell orders, extracting the profit generated by your market impact. This all happens autonomously, orchestrated by smart contracts within milliseconds, entirely within the transparency of the mempool before final inclusion.
It's a sobering reality for a CTO. You are not building applications in a safe, walled garden. You are deploying code into an adversarial arena where predators are optimizing to extract value from your user's public intent.
Which perfectly transitions us to the transaction lifecycle.
Mhm.
To design secure systems, an architect must be able to trace a transaction's journey from the absolute safety of a private key all the way to irreversible settlement. The manual breaks this down into distinct phases.
Phase one is creation and signing. And the text hammers this point home. Signing a transaction is a purely local, offline mathematical operation.
The security implications of this cannot be overstated. Your wallet software constructs the transaction payload, the destination address, the amount, the fee, and then signs it using your cryptographic private key. At the moment of signing, the device does not need to be connected to the internet.
This is the entire foundation of cold storage. You can generate a private key on a laptop that has its Wi-Fi card physically removed. You build the transaction, sign it in a completely air-gapped environment, save the signed output string to a USB drive, and walk it over to an internet-connected machine.
The private key never touches a networked environment. Once signed, phase 2 is broadcast. You inject that signed string of characters into any node on the network.
Phase 3 is validation and gossip. The node verifies the signature math, checks the ledger to ensure you have the funds, and if valid, floods it to the network via the announce then fetch protocol we discussed. The transaction is now sitting in tens of thousands of mempools.
Phase 4 is selection and building. A block producer, whether a miner solving a proof-of-work puzzle or a validator chosen in proof-of-stake, selects your transaction from their mempool, packages it into a block, computes the Merkle root, and finalizes the header.
Phase 5 is append and broadcast. The producer announces their newly minted block to the global network. Every full node verifies it, tears it apart, checks the math, and appends it to their local copy of the ledger.
At this moment, your transaction achieves its first confirmation. If you look at your wallet interface, the status will shift from pending to confirmed.
But the manual is adamant that one confirmation does not mean the transaction is finalized. The text uses a brilliant dirt-shoveling metaphor to explain the concept of depth.
The dirt metaphor perfectly encapsulates the probabilistic nature of security here.
Getting that first confirmation is like dropping your transaction into a hole and throwing a single shovel full of dirt over it. Technically, it is buried, but anyone with a hand trowel could brush that dirt aside and dig it back up. In network terms, an attacker would only need to privately mine a single alternative block to orphan yours and reverse the transaction.
But the protocol doesn't stop. 10 minutes later, another block is mined and chained on top of yours. That is a second, much heavier shovelful of dirt, then a third, and a fourth.
With every subsequent block that gets added to the chain on top of your block, the accumulated weight of the cryptographic work increases exponentially. After 6 blocks, there are tons of earth piled on top. To dig it up now, an attacker would need a massive industrial excavator. They would need to outcompute the entire global network across 6 sequential blocks just to reach your transaction.
This raises an important question for any business accepting crypto payments. At what depth do you stop worrying about someone digging? When is a payment actually irreversibly done?
The distinction between confirmed and finalized has cost crypto exchanges tens of millions of dollars when misunderstood. The manual outlines 2 fundamentally different models of finality depending on the consensus mechanism. The first is probabilistic finality used by Bitcoin.
On a proof-of-work chain, finality is never absolute. It is an asymptotic curve. Every single block added reduces the statistical probability that an attacker could reverse the chain. But mathematically, the probability never reaches 0.
So how many shovelfuls of dirt do we require before we accept the risk?
It is entirely a localized risk management decision based on the financial value of the transaction. If you are selling a cup of coffee, 0 confirmations. Just seeing the transaction pop up in the mempool might be an acceptable risk, knowing a double spend attempt is possible but unlikely for a $3 purchase.
For a $1,000 transaction, you might wait for 1 or 2 confirmations.
Right. But for large-scale corporate settlements, the industry convention on Bitcoin is to wait for 6 confirmations.
Yeah. Given the 10-minute block time, waiting for 6 confirmations means you are waiting an hour for settlement.
After 6 blocks, the sheer amount of electricity required to rewrite the chain makes the probability of reversal practically negligible. That is probabilistic finality. The alternative model is deterministic or economic finality, which is deployed by modern proof-of-stake systems like Ethereum.
How does deterministic finality differ? Does the protocol eventually just declare the block mathematically impossible to reverse?
It doesn't make it physically impossible. It makes it economically ruinous through explicit protocol rules. In Ethereum, validators don't just build blocks. They explicitly vote on specific historical checkpoints. Once a supermajority, specifically 2/3 of all the staked capital on the network, has cryptographically signed an attestation confirming a checkpoint, that block is formally declared finalized.
And if an attacker tries to reverse a block that has achieved supermajority finality?
To reverse it, an attacker would need to convince the 2/3 supermajority to sign a new conflicting history. But if a validator signs two conflicting histories, the protocol slashing mechanism instantly activates. The network mathematically proves the contradiction and destroys the validator's staked collateral.
So it is final because the cost of reversing it requires burning billions of dollars of the attacker's own funds. And on Ethereum, the manual notes this explicit finality checkpoint occurs roughly every 2 epochs, which translates to about 12 to 13 minutes.
The CTO warning here is critical. Do not blindly copy-paste operational rules across different architectures. A 6 confirmation rule on Bitcoin provides an hour of ironclad probabilistic security. Applying a 6 confirmation rule to a chain with a 2-second block time provides only 12 seconds of security, which is highly vulnerable to small network reorgs.
Furthermore, never, ever credit customer accounts based on 0 confirmation mempool data.
Never.
Because if an exchange credits my account instantly while my deposit is still floating in the mempool, I can execute a classic double spend exploit. I can immediately broadcast a second transaction, spending those exact same funds back to a wallet I control, but I attach a massively higher fee. The miners, acting rationally, will grab my second transaction and ignore the first. The exchange just gave me a free credit, and I kept my original funds.
Exactly the scenario you must architect against. You must respect the finality mechanics of the specific chain you are building on.
This entire transaction life cycle, the gossip, the mempool auction, the finality settling, assumes the network is operating smoothly. But distributed networks are inherently messy. What happens when the network stumbles? What happens when 2 nodes shovel dirt onto completely different histories at the exact same moment?
That phenomenon is known as a fork. The term fork is used very sloppily in industry media, but the engineering manual meticulously categorizes them into 3 distinct events. We must separate them. The first and most routine is the accidental fork, or a chain reorganization.
We established that gossip propagation takes a second or 2 to cross the globe. Because of that physical latency, it is entirely probable that a miner in Iceland and a miner in Texas solve the proof-of-work puzzle at the exact same millisecond.
Both nodes construct a perfectly valid block. The node in Iceland broadcasts block A. The node in Texas broadcasts block B. Because of geographical network topology, half the nodes in the world receive block A first, validate it, and append it to their ledger. The other half receive block B first and append it.
The global consensus has just fractured. We have 2 parallel histories. How does a decentralized system resolve a tie without a central referee?
The resolution mechanism is embedded in the client software, the fork choice rule. Nodes are programmed to always follow the heaviest chain, which is defined as the chain with the most accumulated computational work. At the moment of the split, it is a dead heat. The tiebreaker is determined by the next block.
The race continues. Let's say 10 minutes later, a miner in Japan finds the next solution. That Japanese miner happened to see block A first, so they built their new block mathematically chaining it to the header of block A.
As soon as the Japanese miner broadcasts that new block, the block A chain becomes 1 block longer. It now possesses more accumulated mathematical work.
Instantly, every node on the planet that was following the Texas block B chain receives the new Japanese block. They look at the block A chain, run the math, and realize it is heavier. They execute a chain reorganization, or a reorg.
The nodes literally rewind their state. They orphan block B, stripping it away from their ledger. They took all the transactions that were inside block B and dumped them back into their local mempool. Then, they adopt block A and the new Japanese block, realigning with the global consensus.
Block B becomes a ghost. It's referred to as a stale block, or in older Ethereum terminology, an Omer or uncle block. It is perfectly valid cryptographic work that is simply discarded by history.
This routine occurrence underscores exactly why you must wait for multiple confirmations. If your high-value transaction was included in block B but not in block A, a single block reorg just erased your confirmation. You were briefly buried, but the network dug you back up and threw you back into the mempool.
So an accidental fork is a temporary geographic lag issue that resolves itself autonomously. But the other two types of forks are deliberate, human-coordinated upgrades to the protocol rules. The manual defines them as soft forks and hard forks.
A soft fork is defined by its backward compatibility. It is fundamentally a tightening or restriction of the existing consensus rules.
To put that in perspective, anything that is considered valid under the new, stricter rules would also have been considered valid under the old, looser rules.
Precisely the mechanic. If you are operating a node running older software, and you receive a block produced by a miner running the upgraded soft fork software, you will run your validation checks. Because the new rules are just a subset of the old rules, the block passes your checks perfectly.
Yeah.
You remain in consensus without realizing the rules changed. Soft forks only require a supermajority of the block producers to upgrade, not the entire network. Major Bitcoin upgrades like SegWit and Taproot were deployed as soft forks.
I think a great analogy for a soft fork is a web service updating its backend validation. Imagine a website used to accept any password over 6 characters. That's the old rule. They initiate a soft fork upgrade to require a special character. The new rule is tighter. If an older client app sends a password with a special character, the old app thinks it's fine, the new server thinks it's fine. It's perfectly backward compatible. A hard fork, however, breaks that compatibility completely.
A hard fork is a non-backward compatible upgrade. It is typically a loosening of the rules or a fundamental structural change to the data formats.
Sticking with the analogy, a hard fork is like completely changing the API's wire format from JSON to XML. If your old client application tries to parse the new XML server response, it will completely crash. It lacks the vocabulary to understand the data.
In blockchain mechanics, if a hard fork activates, blocks created under the new rules will be explicitly rejected by nodes running the old software. The old nodes will view the new blocks as invalid rule breakers and ban the peers sending them. If the entire community agrees on the upgrade, which happens regularly with scheduled Ethereum updates, then everyone updates their client software. The old rules are abandoned, and the chain continues smoothly.
But the danger of a hard fork arises when the community does not agree.
If the upgrade is contentious, and a significant portion of node operators and miners refuse to install the new software, the blockchain permanently fractures. You now have two parallel networks sharing the exact same history up until the fork block, but diverging into two completely separate realities immediately after.
This isn't theoretical. We saw this in 2017 when Bitcoin Cash hard forked away from Bitcoin over a bitter disagreement about increasing the block size. We saw it in 2016 when the Ethereum community hard forked to reverse the massive DAO smart contract hack, but a group of purists refused the upgrade, continuing the original unaltered chain, which is now known as Ethereum Classic.
For a CTO managing infrastructure, a contentious hard fork is an operational nightmare. Suddenly, your users possess identical cryptographic keys holding assets on both distinct chains. You must immediately architect protections against replay attacks.
A replay attack is fascinating. Because the chains share the same history and key structures, if a user signs a transaction to spend funds on chain A, a malicious actor can take that exact same cryptographically signed packet, broadcast it on chain B, and the network will accept it as valid, spending the user's funds on the second chain without their permission.
Preventing replay attacks requires sophisticated node management and transaction structuring. It's high-stakes digital politics translating directly into engineering crises.
Navigating network lag, routine single-block reorgs, and keeping tens of thousands of global nodes perfectly synchronized. All of these physical realities point directly to why blockchains are so fundamentally limited in their base performance. Which brings us to the ultimate architectural compromise of the manual, the blockchain trilemma.
We have to confront the physical limits of the universe. The performance of a blockchain base layer is governed by two main parameters: block time and block size.
We noted earlier that Bitcoin limits its block time to 10 minutes, and Ethereum targets 12 seconds. If we want higher throughput, why not simply alter the protocol variables to produce a block every 100 milliseconds?
Because you cannot outrun the speed of light. It takes physical time for data packets to hop through fiber optic cables across the globe. If you tune the protocol to produce blocks faster than the gossip protocol can propagate them to the edges of the network, you will trigger a catastrophic cascade of accidental forks. Thousands of miners would constantly be building on stale tips, completely unaware of each other's progress. The network would waste immense amounts of energy resolving constant reorgs and would struggle to ever converge on a single secure truth. You must give the network breathing room to synchronize.
Okay, if the speed of light prevents us from lowering the block time, why not attack the other variable? Let's increase the block size. Bitcoin hard caps its blocks at roughly 1 to 4 megabytes. Ethereum restricts computation via a gas limit per block. Why not configure the protocol to accept 10 gigabyte blocks? You could shove millions of transactions into every single batch and solve the scaling problem overnight.
Increasing block size introduces two fatal flaws. First, a 10 gigabyte block takes a significant amount of time to transmit over standard consumer broadband connections, which again exacerbates the propagation latency and increases accidental forks. But the second reason is the fatal blow. Remember the role of the full nodes.
The deeply paranoid independent auditors who verify the entire history.
Exactly their role. Every full node operator has to download, process, and permanently store every byte of that block. If the protocol demands 10 gigabyte blocks every 10 minutes, the storage and RAM requirements for running a node would grow by terabytes every week. Very quickly, the hardware demands would exceed the capacity of consumer laptops and desktop computers.
And if an ordinary citizen can no longer afford to run a full node, they drop off the network. The only participants left who can afford the enterprise-grade hardware to validate the chain are massive data centers, cloud providers, and wealthy corporations.
And the moment you restrict validation to a handful of powerful centralized operators, you have completely sacrificed the decentralization and censorship resistance that justified building the blockchain in the first place. You have effectively reinvented the traditional centralized database, just burdened with highly inefficient cryptographic steps. This inherent, unavoidable dynamic is formally formalized as the blockchain trilemma.
The trilemma dictates that in a distributed network, you can only optimize for 2 out of 3 properties: decentralization, security, and scalability. You cannot maximize all 3 at the base layer.
Bitcoin and Ethereum's core developers made a deliberate architectural choice to prioritize decentralization and security. They intentionally restrict block sizes and times to ensure that the hardware requirements for running a full node remain accessible to average individuals worldwide. The inescapable mathematical consequence of optimizing for decentralization is painfully low throughput.
Let's contextualize that low throughput with the numbers from the manual, looking at early 2026. Bitcoin's base layer maxes out around 5 to 7 transactions per second globally. Ethereum's layer 1 processes around 15 to 30 TPS. To put that in perspective, a centralized payment network like Visa handles tens of thousands of transactions per second without breaking a sweat.
But inevitably, CTO will encounter marketing materials for alternative Layer 1 chains like Solana, which boast 1,000 to 3,000 plus TPS directly on the base layer. It is crucial to understand how they achieve that.
They didn't magically break the mathematical laws of the trilemma.
No, they simply chose a different point on the trade-off triangle. Chains that push massive scalability at the base layer do so by demanding extremely powerful, expensive server-grade hardware and massive bandwidth to run a validator node. They are intentionally trading away a degree of pure decentralization, making it harder for average users to audit the network in order to purchase high throughput. It is a valid architectural choice, but it must be recognized as a trade-off, not a miracle.
So if pure, highly decentralized base layers like Bitcoin and Ethereum are structurally constrained to a few dozen transactions a second, how does this industry ever expect to scale to support global daily commerce?
The engineering consensus detailed in the manual relies entirely on Layer 2, or L2, scaling solutions. The underlying philosophy is simple. Do not execute heavy, high-volume day-to-day transaction processing on the congested main chain.
Instead, you push that execution off-chain. You build a secondary, vastly faster network built on top of the Layer 1.
You execute tens of thousands of transactions rapidly and cheaply on the Layer 2 network. Then, the L2 uses advanced cryptographic proofs to compress all of that activity into a tiny summary. It takes the result of those thousands of transactions and posts, just that cryptographic proof, back down to the Layer 1 base chain for permanent, secure settlement.
I think of it like a crowded casino. You have thousands of people playing blackjack, trading chips back and forth at high speed all night long. The casino doesn't call the main bank vault after every single hand to update the ledger. They process the high-volume activity locally. Then, at the end of the night, they tally up the net results and settle one final, compressed transaction with the main bank vault.
That analogy perfectly describes technologies like Ethereum Rollups networks like Arbitrum, Optimism, or Zscaler Sync, and Bitcoin's Lightning Network. These L2 solutions achieve effective throughputs in the tens of thousands of TPS, while mathematically anchoring their final security and immutability to the decentralized L1 base layer.
So the source manual leaves its technical readers with a piece of vital armor to defend against industry marketing. If a salesperson approaches the CTO pitching a revolutionary new blockchain that processes 50,000 transactions per second, the CTO needs to ask three specific questions.
First, inquire about the finality time. Bragging about 50,000 PPS is irrelevant if it takes 30 seconds for those transactions to achieve irreversible finality. Second, ask for the exact hardware requirements to run a full node. If it requires a $20,000 server rack, the network is centralized and you should question its censorship resistance. Third, clarify the architecture. Is this a base layer 1 network, or is it a layer 2 rollup that relies on a more decentralized chain for its ultimate security?
If you don't ask those hard engineering questions, you might be tricked into buying a very slow, very expensive, heavily marketed traditional database.
If we synthesize this entire engineering manual, the grand takeaway is that a blockchain is, at its core, a Byzantine fault-tolerant replicated state machine. It purchases the properties of trustlessness and censorship resistance by spending computing performance and storage capacity with absolute abandon. Every limitation that frustrates users, the agonizing wait for block confirmations, the exorbitant gas fees during congestion, the strict block sizes, these are not software bugs. They're deliberate, unavoidable design compromises required to keep the system decentralized.
We have covered an immense amount of technical ground today. We stripped away the financial noise and looked at the actual data structures. We dissected the headers and bodies and traced how the Merkle roots and avalanche-sensitive hashes create an economically tamper-evident chain of wax-sealed envelopes.
We mapped the network topography, contrasting the paranoid, verifying full nodes against the lightweight SPV clients that rely on Merkle proofs. We analyzed the announce then fetch gossip protocol that keeps bandwidth manageable.
We waded into the dark forest of the mempool, exploring how block space scarcity creates an adversarial auction where MEV bots execute sandwich attacks in milliseconds. We followed a transaction from its air-gapped offline signature through the probabilistic dirt shoveling of Bitcoin confirmations to the explicit economic finality and slashing mechanics of proof of stake.
And finally, we confronted the physical limitations of the trilemma, understanding why base layers must remain slow to prevent forks, pushing the future of scalability onto compressed Layer 2 networks.
It is a profound shift in how we engineer trust in digital environments. And that leads me to a final thought I want to leave you, the listener, with today. Something to mull over that builds on these incredible rigid trade-offs we've explored. We have established that these decentralized base layers are intentionally slow, highly secure, purely trustless settlement layers optimized for human-driven nodes. But looking slightly ahead, what happens when millions of non-human entities like autonomous AI agents need to execute microtransactions with each other autonomously?
That is a fascinating and imminent horizon for network architecture.
Autonomous AI agents cannot walk into a traditional bank branch, show an ID, and sign a legal contract to open an account. They do not possess social security numbers. To participate in commerce, they will absolutely require a natively digital, permissionless, trustless base layer to hold and transfer value. But will these autonomous programs be content relying on the Layer 2 roll-up solutions we rely on today? Or will the sheer, unfathomable volume of continuous, high-speed machine-to-machine commerce force the invention of an entirely new consensus model that somehow shatters the constraints of the current trilemma?
Accommodating machine-to-machine economic velocity is the challenge that will redefine distributed systems engineering over the next decade.
We started today by talking about a database as a pristine, highly guarded fortress controlled by a single king. We've seen that the alternative is a chaotic, noisy, global public square where thousands of strangers agree on the truth using nothing but cryptography and economic incentives. As autonomous AI enters that public square, the noise and the volume are only going to amplify. Thank you for joining us on this deep dive into the source material. Keep questioning the physical limits and the underlying math behind the buzzwords, and we'll catch you next time.